Hi, everybody. It's Professor Mitchell, continuing with Chapter 5. Today, we're looking at Section 5.5 on negative exponents and scientific notation. In this section, we will simplify expressions containing negative exponents, use all the rules and definitions for exponents to simplify exponential expressions, write numbers in scientific notation, convert numbers from scientific notation to standard form, and perform operations on numbers written in scientific notation. And we're still working on SLOA, which is to perform mathematical operations on algebraic expressions. All right, so we'll start with a summary of the exponent rules that we learned in section 5.1. which you see here. Number 1 is the product rule. Number 2 is the quotient rule. Number 3 is the power rule. Numbers 4 and 5 are the product to a power rule and the quotient to a power rule. And then finally, number 6 is the zero exponent rule. And I had mentioned back in 5.1 that there was a rule number 7 coming. So that's where we're going to pick up this rule. And that is the negative exponent rule. So suppose that I asked you to simplify the expression x squared over x to the 6th. There are 2 ways you could do that. One way is without even knowing any exponent rules, you could just use the fact that x squared is x times x to the 6th is x times x times x times x times x times x. You cancel 2 pairs of x's, and you're left with 1 over x times x times x times x, which is 1 over x to the 4th. So that's one way to do it. Another way is to use the quotient rule, which would tell you that x squared over x to the 6th is x to the power 2 minus 6, which is x to the negative 4. So if you do the problem one way, you get 1 over x to the 4th. If you do it a different way, you get x to the negative 4. Assuming that both of those ways are correct, which they are, that must mean that x to the negative 4 and 1 over x to the 4th are the same thing. And that gives us the negative exponent rule, which says that for any real number a not equal to 0, a to the power negative n is equal to 1 over a to the n. In other words, a to the negative n is the reciprocal of a to the n. All right, so if you have to remember the negative exponent rule in one word, that one word would be reciprocal. All right, so here is our first batch of examples. So we'll go over these 3 examples, and then I'll tell you about a couple of shortcuts that come from 2 of those examples. So let's go over to the tablet. And our first example is 4 to the negative 1 plus 4 to the negative 2. All right, so according to the rule that we just looked at, 4 to the negative 1 is the reciprocal of 4 to the 1, and 4 to the negative 2 is the reciprocal of 4 squared. So believe it or not, 4 to the negative 1 plus 4 to the negative 2 means 1/4 plus 1/16. All right, so this is just an adding fractions problem. In order to add these fractions, we need a common denominator. That common denominator would be 16. So we'll multiply the top and the bottom of this one by 4. And that gives us 4/16 plus 1/16, which is 5/16. All right. Possibly not the answer you were expecting. All right. I think that one's kind of surprising. Letter B, we have 2/5 to the power negative 2. So this is one example that's going to lead to a shortcut. In the meantime, using the negative exponent rule, which again is a to the negative n equals 1 over a to the n. playing the role of A in this problem is 2/5. So I just want to point out to you that when I go to write this as 1 over A to the n, the 2/5 is still going to be 2/5. The only thing that's going to change is the exponent. It's going to change to a 2. All right, so using exponent rule number, I believe it's 5, the quotient to a power rule, 2/5 squared is 4 over 25. So we're dividing by 4 over 25, which is the same thing as multiplying by 25/4. So it turns out that 2/5 to the power -2 is 25/4. That would be my official answer. I just want to point out to you, to help the shortcut make a little bit more sense, note that 25/4 is 5/2 squared. Not making that part of my answer, just pointing out that that's what it is. Okay. All right, and the last example in this batch is -1 over y to the -6. So again, according to the negative exponent rule, y to the -6 is 1 over y to the 6th. Just changed this into this. Nothing else in the expression changes. So we're dividing by 1 over y to the 6th, which is the same thing as multiplying by y to the 6th over 1. And my final answer would be -y to the 6th. All right. So what I want you to notice in this one is that the y to the -6 in the denominator eventually turned into y to the 6th in the numerator. And that deals with the other shortcut that I'm going to tell you about right now. Okay, so letter B, we had 2/5 to the -2, and that turned out to be 5/2, the reciprocal of 2/5 to the power 2. In general, whenever you have a fraction to a negative number exponent, you can rewrite that as the reciprocal of the fraction to the positive exponent. Okay, so if I had known that before I did letter B would have gone a little faster. And then shortcut number 2, this comes from example C. So we already know that a to the -n is 1 over a to the n. In other words, to make a negative exponent positive, if the negative exponent is upstairs, you send it downstairs. Well, the reverse is also true. If the negative exponent is downstairs, you can send it upstairs. Okay. So you'll see me making use of these shortcuts in future problems. All right, so let's see what else we have. Okay, so now we have our complete list of exponent rules, the same rules 1 through 6 that we learned earlier, and now we have rule number 7, which is the negative exponent rule. All right, so now we have another batch of examples. These are getting a little fancier now. All right, and of course I have these all written out on the tablet, so let's go back there. And we will start with p over p to the -3, q to the -5. So right away, I'm going to use one of my shortcuts. Since I see a couple of negative exponents downstairs, I am going to send them upstairs. And those exponents will become positive. So now actually everything will be upstairs. And nothing will be left downstairs, which means a 1. Put a 1 down there. All right, and then by the product rule for exponents, rule number 1, P times P to the third is P to the fourth. So I'm just going to write this answer as P to the fourth times Q to the fifth. And that's it. So that's a pretty easy one. All right, next we have negative 5, a to the fourth, b to the negative 7, times negative a to the negative 4, b to the third. This is very similar to some problems that we did in section 5.1, except that in 5.1, none of the exponents were negative. So we'll start by multiplying the coefficients. Negative 5 times negative 1 is 5. And then using the product rule, a to the fourth times a to the negative 4 is a to the power 4 plus negative 4. And by the product rule again, b to the negative 7 times b to the third is b to the power negative 7 plus 3. All right, so cleaning that up, we get 5 times a to the 4 plus negative 4 is 0. Negative 7 plus 3 is negative 4. All right, so one of the rules for making your expression completely simplified is that you don't have any zero exponents, because we have the zero exponent rule. We can just change this a to the 0 into 1. And another rule is that we don't have any negative exponents. If the negative exponent is upstairs, we send it downstairs. If it's downstairs, we send it upstairs. In this case, it's upstairs, so I'm going to send it downstairs. So my final answer would be 5 over b to the fourth. All right, now they're getting fancier and fancier. In letter C, we have the negative 3 power of r times s divided by the square of r squared times s cubed. So what I'm going to do is use the product to a power rule, rule number 4, to put this negative 3 power here and here. So that gives me r to the negative 3, s to the negative 3. All right, and then again, using the product to a power rule, put the square here and here. And in this one, I'm also using the power rule, because the first thing I get there is r squared squared. R squared squared is r to the fourth, because we multiply the exponents, right? S to the third squared is s to the sixth. All right, so at this point, once I've knocked down all the parentheses, I'm going to look for negative exponents. I see 2 negative exponents. I'm going to send them downstairs, which leaves nothing upstairs, which means 1. So we have r to the third times r to the fourth, s to the sixth times s to the third. And finally, using the product rule, that comes out to 1 over r to the 7th times s to the 9th. All right, and for the last example, we have the 4th power of a to the 6th times b to the negative 2 divided by the 3rd power of 4 a to the negative 3 b to the negative 3. This one is pretty similar to letter C, so I would encourage you to pause the video, try this one, come back and compare notes. All right, so hopefully you tried this one. We're going to start by putting the 4th power on each of these factors and put the 3rd power on each of these factors, including the 4. I've seen this happen many times. For some reason, when students see a regular number inside there, they don't realize that the exponent also goes on that number, but it does. All right, so we're going to end up with a to the 24th, right? 6 times 4, times b to the negative 8, over 4 to the third, which is 64, a to the negative 3 times 3, which is negative 9, and b to the negative 3 times 3, which is negative 9. All right, so now I see 3 negative exponents. These two both have to go upstairs. This one has to go downstairs. So that's going to give me a to the 24th times, I'm going to write the ones that have moved in a different color. A to the 9th, b to the 9th. And then downstairs we have 64, and then a new b to the 8th. All right, so we can clean that up just a little bit more. Using the product rule, we can put these two together. A to the power 24 plus 9 is 33. And then using the quotient rule, b to the 9th divided by b to the 8th is b to the power 9 minus 8, which is 1. So final answer is a to the 33 times b over 64. All right, back to the presentation. I think this is the time where I tell you about another shortcut. Yes. Okay. So whenever you have common factors on the top and on the bottom, here are a couple of examples. B to the 9th divided by b to the 8th, which we just had in that example, simplifies to b to the power 9 minus 8, which is b to the 1st. But if I had something like c to the 8th divided by c to the 13th, using the quotient rule, that's c to the power 8 minus 13, which is c to the negative 5. But then I would have to rewrite that as c to the 5th. So the shortcut, which works well in problems like this second example, is just whenever you see two powers of the same variable on the top and the bottom, just subtract the smaller power from the larger power and leave the remainder where the larger power was, which will sometimes be upstairs and will sometimes be downstairs, right? And that way you can avoid ever having to see a negative exponent, which you're going to have to simplify anyway. All right, so now that brings us to scientific notation. A number is written in scientific notation when it has the form a times 10 to the power n, where a is a real number between 1 and 10. It can be 1, it cannot be 10. It has to be strictly less than 10. And n is an integer, all right? So another way to talk about this real number a is that if it is a decimal, the whole number part of the decimal has to be something from 1 to 9. Okay, it can't be any smaller than 1 and it can't be any bigger than 9. Scientific notation is used to write very large and very small numbers to make them easier to read, because otherwise the number is going to have a whole bunch of zeros in it. And if you had seen me preparing to make this video, I was looking at one of these numbers and I was squinting at it, not because the type was too small, but just because there were too many zeros on it and it was all kind of blending together. Here's a cute little, this is a very old school meme, isn't it? With that colored background with the triangles. That I think is back to like the, I don't know, 2006 or something. I found it a little more recently than that, but I know that's a very old meme format. Scientific notation because my account balance won't fit on the paper. Wouldn't that be nice? All right, so we'll start with converting from scientific to standard notation, which is a little easier than going the other way. All right, so here are the two examples. To convert to standard notation, we have 4.8 times 10 to the negative 6. And we have the current population of Earth as I make this video. Today is February 16th, 2022. I looked this up last night. And as of yesterday, the population of Earth was estimated to be 7.83 times 10 to the ninth. Every time that I give this lecture, I update that number. The last time I had updated it before this was in 2017. At that time, the population of Earth was about 7.5 times 10 to the ninth. So it has grown since then. Let's go over to the tablet. And I'll show you how this works. Okay, so first we have 4.8 times 10 to the negative 6. When you see a negative exponent, that means to move the decimal point to the left. So a negative 6 means move the decimal point 6 places left. 1, 2, 3, 4, 5, 6. All right, and there you have it. So this number written in standard notation would be 0.00000048. When I teach pre-algebra, we play a little game in the pre-algebra class, which is that I toss out little amounts of extra credit for students who read the decimals correctly, the way that they're supposed to be read. This one would be read, and I have to think about this when the number gets this small. If the decimal point was here, that would be hundredths, 48 hundredths. So this would be thousands, 10 thousands, 100,000s, millions, 10 millionths. So this decimal is 48 10 millionths, 48 parts per 10 million. That is a very, very small amount. All right, as opposed to this number, which is a pretty big number, the positive exponent means move the decimal point 9 places to the right. So I start with 7.83. And I go 1, 2, 3, 4, 5, 6. Oh, darn it. When I hold the pen down too long, it changes it into a line. So let me try that again. 1, 2, 3, 4, 5, 6, 7, 8, 9. Pick up the pen. Okay. Fill that in with zeros. All right, so what we end up with, I'm just going to stick some commas in here. I'll rewrite this answer so it looks prettier. 7,830,000,000. Okay, so I mentioned last time I did this in 2017, it was 7.5 times 10 to the ninth, which would be 7,500,000,000. So the population of Earth in the last 5 years has grown by approximately 330 million, which I think is pretty close to the population of the United States. Just to put that in perspective, we've added another United States in the last 5 years. All right, back to the presentation for a couple of examples of going the other way. Converting from standard to scientific notation, we have sorry, I keep getting this window pop up. All right. 0.000000017. That's the one that I was squinting at before. And 20 million, the temperature in degrees Celsius at the center of the Earth. So if you live in the Central Valley of California and you complain about the heat in the summer, which I know I do, stop whining. It's not that hot compared to 20 million degrees Celsius. Okay, so back to the presentation. So when you're converting from standard to scientific notation, what is very helpful to remember is that numbers, scientific notation numbers with negative exponents are small numbers. Scientific notation numbers with positive exponents are large numbers, because some of the most common mistakes with scientific notation, you'll put a positive exponent when it should be negative, or a negative when it should be positive. But if you remember this, that should make those mistakes easy to catch. Okay. So the way that I like to do this is to, first of all, figure out where would the decimal point have to go in order to make correct scientific notation. Remember, that number that sits in front has to be between 1 and 10. So that means the decimal point should go between the 1 and the 7. All right, and this is a very small number, which means it's going to be 1.7 times 10 to a negative exponent. So if the decimal point was here, we would go 1, 2, 3, 4, 5, 6, 7. And this number written in scientific notation is 1.7 times 10 to the negative 7, which is 1,700 millionths. So that's an even smaller number than 48 10 millionths. All right, and then the next example, 20 million. When you don't see a decimal point, that means it's at the end of the number. Where would it have to go in order to make correct scientific notation? It would have to go right after the 2. All right, so then to get it where it's supposed to be, we would go 1, 2, 3, 4, 5, 6, 7. And this number written in scientific notation is 2 times 10 to the 7th. All right, so I think that just leaves one more thing for me to show you, which is doing operations with scientific notation. All right, so I'll just show you the examples. We're going to evaluate the following expressions and write the answer using standard notation. So first we have 5 times 10 to the 6th times 4 times 10 to the negative 8th. So a very big number times a very small number. Imagine if those numbers were written in standard notation. It would be 5 with a bunch of zeros times 0.0000, a bunch of zeros, and then a 4. That would drive me crazy trying to multiply them that way. It's much easier to multiply them in this form. And then a division example. This is the quotient of 2 small numbers. All right, so back to the tablet one last time. And we start with 5 times 10 to the 6th times 4 times 10 to the negative 8. So it's very easy to simplify these. Just do 5 times 4 times, and then use the product rule to simplify 10 to the 6th times 10 to the negative 8. You would add the exponents, 6 plus negative 8. 5 times 4 is 20. 6 plus negative 8 is negative 2. Now, this is not correct scientific notation because 20 is not between 1 and 10. But the good news is that they asked for it to be written using standard notation. So we can just do what we were doing before, take the decimal point, which is here, and move it 2 places to the left. So the answer written in standard form is just 0.2 or 2/10. All right. And for the last example, we have 2.5 times 10 to the negative 4 divided by 5 times 10 to the negative 9. So what I would suggest is have these two switch places because they have negative exponents. And we'll do 2.5 divided by 5 times 10 to the 9 divided by 10 to the 4. 2.5 divided by 5 is 0.5. And by the quotient rule, 10 to the 9 divided by 10 to the 4th is 10 to the 5th. Again, not correct scientific notation because 0.5 is not between 1 and 10, but it doesn't matter because we can just take that decimal point and move it 1, 2, 3, 4, 5, which gives us a final answer of 50,000. And that is going to do it for section 5.5. We'll see you next time.